Hello everyone, I am Priyanshu Singh, and in this presentation I am going to talk about quantum computing. So without any delay, let's go to the topic. So the first question you will arise, what is quantum computing? So the quantum computing is an area of computing focused on developing computer technology based on the principles of quantum theory, in which it explains the behavior of an energy material on the atomic and subatomic levels. Or we can say that quantum computing is a type of computation that harnesses the collective properties of quantum states such as superposition, interference, and entanglement to perform the calculation. The devices which is used to perform the quantum computers are known as quantum computers. Two, the current quantum computers are too small to outperform usual computers for practical applications, but they are believed to be capable of solving certain computational programs such as integer factorization, which is faster than the classical computers. Now, why we need quantum computing? So the quantum computers are aiming to utilize these capabilities to become highly efficient as they use quantum bits or qubits instead of the simple manipulation of ones and zeros. Qubits or quantum bits are units of quantum information and a two-state quantum mechanical system. Quantum computing is said to be more power efficient than modern computing through the use of quantum tunneling. They are expected to reduce power consumption from 100 to 1000 times. Cold temperatures is needed for stable quantum computers. Quantum computers could speed up learning process of artificial intelligence, reducing the thousands of years of learning to mere seconds. Certain tasks such as emailing aren't as suitable for quantum computers, which is why modern computing isn't set to be replaced by quantum computers. The latter are used to solve highly complicated programs. So, the quantum computers have the potential to revolutionize the computation by making certain types of classically intractable problem solvable. Now, let's go to the application of quantum computing. So, the first use of quantum computing is in the field of artificial intelligence. Now, the quantum computing potentially opens up the new opportunities in artificial intelligence, which often involves the computational process of very large quantities of data in order to make better prediction and decisions. A growing research field in quantum machine learning identifies the ways that quantum algorithm can enable faster artificial intelligence. The current limitation on the technology and software make quantum artificial general intelligence a fairly remote possibility, but it certainly makes thinking machines more than a subject for a science fiction. Now, the second application of quantum computing is in the financial services. Finance was the one of the most earliest domains to embrace the big data, and much of the science behind the pricing of complex assets such as stock options, etc., involves combinatoric calculations. Now, the third application is the complex manufacturing. Quantum computers can be used in taking large manufacturing data sets on operational failures and translating them to combinatoric challenges. When paired with a quantum inspired algorithm, it can identify which part of a complex manufacturing process is contributed to incidents of product failure. For product like microchips, where this production process can have thousands of steps, quantum can help to reduce its cost failures. Now, let's talk about qubit or quantum bit. So, it is a basic quantum mechanical analog of classical bit. In classical computing, the information is encoded in bits where each bit can have the value 0 or 1. But in the quantum computing, the information is encoded in qubits. A qubit is a two-level quantum system where the two basic qubit states that are usually written as denoted here as in the format 0 and 1. A qubit can be in the state 0, 1 or in a linear combination of other both the states. Now, let's talk about the single qubit computational basic states. The two orthogonal Z-basis state of qubit are defined as 0 and 1. When we talk about So when we talk about the qubit basic states, which we implicitly refer to the Z basic states and as the computer basic states, can be denoted by this. So now let's talk about the types of qubits. There are mainly many kinds of qubits. Some occur naturally and others are engineered. Some of the most common types include the spin, trapped atoms and ions, photons, and superconducting circuits. Now let's talk about spin qubits. In this, the most quantum particles behave like little magnets. We call this the property spin. The spin orientation is always pointing either fully up or fully down, but never in between. Using these spin states of up and down, we can build a spin qubit. In this, 0 points to the pointing up and 1 points to the pointing down. And the next one is the trapped atoms and ions. We can use the energy levels of electrons in a neutral atom or ions as qubits. In their natural states, these electrons occupy the lowest possible energy levels. Using the lasers, we can excite them to the higher energy level. We can assign the qubit value based on their energy state. The denotion of the trapped atom ions in this is the 0 represents the low energy state and the 1 represents the higher energy state. Now, the next one is the photons. So, we can use photon, which are individual particles of light, as qubits in several ways. They are the polarization qubit, the path qubit, and the time qubit. Now, in the polarization qubit, each photons carries an electromagnetic field with a specific direction, known as its polarization. The two states is used to define the qubits are horizontal polarization and vertical polarization. In polarization qubit, 0 represents the horizontal and 1 represents the vertical. Now talking about the path qubit, the path of a photon takes is another way to define a qubit. We can actually put up a photon in superposition of being here and there by using a beam splitters. In the path qubit, 0 represents the top path and 1 represents the bottom path. Now the last one is the time qubit. In the time qubit, it is also possible to build a photon qubit use its time of arrival. We can create a quantum superposition of a photon arriving early and a photon arriving late. In this case, the time qubit 0 represents the photon which is arriving early and the 1 represents the photon which is arriving later. Now, the next one is the superconducting circuits. When we cool to a lower temperature, some materials allow an electrical current to flow with no resistance. We call these as superconductors. We can design electrical circuits based on superconductors to behave like qubits. Unlike the other examples of qubits, these are fabricated systems which are made of billions of atoms. However, they still behave as a single quantum system. One, the way we can build a superconducting qubit is by assigning a value to a direction that the current flows around an electrical circuit. Here, the 0 represents the clockwise current and the 1 represents the counterclockwise current. Now, let's talk about how we are trying to get. Now, building quantum computers is incredibly difficult. Many candidates qubit system exist on the scale of single atoms, and the physicists, engineers, and material scientists who are trying to execute the quantum operations on the systems are constantly dealing with two competing requirements. The first one is the qubits needs to be protected from the environment because it can destroy the delicate quantum states needed for computation. The longer a qubit survives in its desired state, the longer its coherence time. From this perspective, isolation is prized. Now, the second is, however, for an algorithm, execution qubits needs to be entangled, shuffled around physical architectures, and controllable on demand. The better this operation can be carried out on higher their fidelity, balancing the required isolation and interaction, which is difficult. But after decades of research and a few systems are emerging as top candidates for a large-scale quantum information processing. Here, in this, the superconducting systems are trapped atomic ions and semiconductors are some of the leading platforms for building the quantum computers. Each one has an advantage and disadvantage related to coherence, fidelity, and ultimate scalability to large system. It is clear, however, that all of this platform will need some type of error correction protocol to be robust enough to carry out meaningful calculation, and to implement this protocol is itself a large area of research. Now, let's talk about the advantages of the quantum computing. So the main advantage of quantum computing is that it is even the classical algorithm calculation. They are also performed easily, which is similar to the classical computer. If we add the qubits to the register, we increase the storage capacity exponentially. In this computing, qubit is the conventional superposition state. So there are advantage of exponential speed up to resulted by handle the number of calculation and method. In this, the computing required a very less power. The other advantage of quantum computing is it can execute any task very faster and very accurately compared to a classical computer. Generally, the atom changes very faster in the case of traditional computing, whereas in quantum computing it changes even faster. Now, let's head towards the disadvantage of quantum computing. Qubits are not digital bits of base, thus they cannot use as conventional error correction. The main disadvantage of quantum computing is the technology required to implement a quantum computer is not available at the present days. The minimum energy requirement for quantum logical operation is 5 times that of classical computers. The quantum CPU will have the efficiency and heating problems of its own, which can affect the efficiency of the quantum computing. When a measurement of any type is made to a quantum system, the decoherence is totally broken down and the wave function collapses into a single state. So, for this presentation, these are the references which I have took to make this PPT. So, that's all for the presentation. Thank you.